or you just name it, any of those computationally intensive processes, uh, we would be kind of like talking about how to leverage GPU. So for this session, I am going to record this. Let me go ahead and start the recording first. Let's see if I can do that. All right, it seems that the recording is started, so we're good. And this recording would also be available after the session. So as I was saying, we would see how we can speed up those signal processing, image processing kind of algorithms on GPU. So that being said, uh, I'm Akhilesh Mishra, and I'm a senior application engineer based off at the MathWorks USA office. And I work very closely with our partner company, TechSource, uh, who provides you the licenses and is your business point of contact in the Singapore region, in the ASEAN region. And I would be presenting the seminar today, but for any follow-up questions or you need some more information on trials about the products being discussed today, so your point of contact would be the TechSource guys as well as the Syndas systems. So, that being said, so let's dive in those 7 practices or the Holy Grail. So I mean, I do call it 7 practices, but essentially what we'll cover is like, just explore what are the different options of using and leveraging GPUs. So one of the things, the first thing is going to be speeding up algorithms using features from a toolbox called Parallel Computing Toolbox. So we'll see how the Parallel Computing Toolbox has those GPU functionalities. Then we'll go and see how we can generate CUDA code to speed up algorithms using GPU Coder Toolbox. And then we'll also dive into how do we further optimize the generated code to further speed up and the performance of our generated CUDA code from the algorithms. Then we'll also cover some workflow on how to deploy standalone CUDA code on embedded GPUs. So if you're working on embedded GPUs, I'll talk about that. And if you do not know what's the difference between embedded GPU and a desktop GPU, I would be talking about it just in a bit. Then we'll also see how we can leverage MATLAB to verify and validate your algorithms on the embedded GPUs, on the CUDA code in parallel. Then finally, I'll also cover like how we can leverage the GPU on the cloud for speeding up computations with 2 different workflows. So all this I would cover with keeping in mind one of a very basic, simple example. So I just, because, radars, ultrasound, like signals, uh, the processing is intensive. So I take this example from a seismic survey of a ground penetrating radar signal processing, like as a case study. So what happens in this, just at a very high level. So those of you who do not know the domain of radars, you do not need to worry. But really what happens is there are some sensors above the surface of the Earth. They're transmitting signals below the Earth, and then we get the reflections back. And then there's a whole lot of processing, and which finally results in images like this sort, where you can see that these are the layers of the rocks, uh, the subsurface layers, and then there are some features like which start showing up, like there's an asphalt deposition or there's some a lake in this case or whatnot. So basically, like signals getting transmitted below the ground, they're getting received back. And once they receive back, there goes through a series of processing. There's a match filtering. There's a pulse compression, there is some migration algorithms and whatnot. So a big series of algorithms, and we'll see like how will one of those algorithms processing chain, which is actually a part of a ray tracing algorithm for this particular scenario, can be sped up using GPU. So I'll use that as a case study. But the reason we're using GPUs is because in this one of those ray tracing methods, there's a lot of processes. Like it's a matrix. which is the raw data coming in. Then there's a transposition problem. Then there's FFTs involved. Then there's, some migration. There's range compensation. There's a multiplication by exponential. Uh, um, um, yeah, a bunch of mathematical operations. So even though we're taking a case study of a radar example in this case, but this is a very generic workflow and can be applied to any of the signal processing or image processing involving filtering or complex arithmetics or linear algebra kind of problems, which can be scaled massively parallel on a GPUs. So that being said, really quickly, just to define the scene which I have synthesized. So what I do is I create in MATLAB a scenario with a moving array above a ground surface, and I say that, hey, just for my simulation sake, I have only 3 targets inside the Earth, let's say at 200 meters, 400 meters, 700 meters. So I'll be simulating rays, receiving it back. And then, as this geophone arrays move in this direction, like doing the scanning of the imaging ground, I would just try to do the processing in such a way that I'll implement one of the focusing algorithms. So what that really does is once I collect the rays, uh, because my, oops, um, because my ground penetrating radar is moving in this direction. So when my radar is over here, the signals kind of get reflected back the first target, the second target, as well as the third target. Then my signal, when it's here, it gets reflected off first target, second target, and third target. So basically, as it kind of goes along this entire path, we get the return signals throughout. Like, we get some intensity returns, and it's very strong in the center. It's kind of like fades away towards the edges because of the antenna pattern. And what this algorithm does, this focusing algorithm, which I would be talking about, is it does, focusing in these 3 stages. The first stage is pulse compression, where this wide beam kind of gets compressed to thin lines, but then these are like parabolic structures for the point targets. But then I implement this time domain back projection, which is a ray tracing algorithm to finally focus these targets, these parabolas into nice point targets with some side lobes. So that's one of a very standard algorithm, but we'll see that it's implemented using for loops, it's implemented using FFTs, it's implemented using, exponential multiplications, and we'll see how we scale up in GPUs. So that being said, uh, parallelizing processing with GPUs, a little bit about GPUs. So that is the problem or the use case which we'll be going over today with the 7 best practices. But for this parallelizing processing with GPUs, just to give you a sense what GPU is, under the hood GPU, you can think of it as a multiple core computer. But in this case, it's not 4 cores or 8 cores. It's like 1,000 cores, 2,000 cores, or whatnot. So that's like the hardware standpoint. And from a software standpoint, what really happens is, so the way the things are processed in the GPU is, at a thread level. So there's like processes launched on each of these cores in a grid and a block kind of format. And these processes, these parallel processes, all these threads like run all together at once in parallel, and that kind of helps like speeding up. So there are like thousands of threads launched all together at once to be able to run in parallel, and then get a very, very fast speed up. So speaking of that, types of GPUs. So I said in the beginning, there are 2 types of GPUs. One is desktop GPU and one is embedded GPUs. So the desktop GPUs are the one which are connected with your desktop, like, like an operating system. And then the way it works is the GPU memory actually speaks or talks with the RAM on your system. And then there's a data exchange between those, and then it processes all the faster execution things and whatnot. But on the embedded SoC system GPUs, what really happens is these are like meant for standalone deployment and edge deployment. For example, like if I were to have a real-time system, uh, real-time system kind of deployed on the field, then I would generate CUDA code and put it on the GPU, which is on the embedded platform. Those are like small targets, so they can kind of go together with any hardware or end computing device, almost the size of a a palm or like a standard chip or whatnot. So this is like one of the embedded GPUs, which is a Nano, and it's the size is, I mean, if you guys have seen an Arduino board, so this Nano is almost the size of the Arduino board, and it has a like a GPU and a CPU device, just in this small piece of hardware. So it is used for uh, deployment on the edge devices. But the question here is now, how does MATLAB fit in? So the MATLAB really offers this parallel solution or the GPU solution to basically like three different pathways. So the first pathway is the parallel computing toolbox, which is one of the first things which we'll discuss. Then the other pathway is like how we can use GPU coder to convert this MATLAB code to .cu files or the CUDA code and run those on the embedded as well as the desktop GPUs. But then finally, with MATLAB Parallel Server, we can exploit the GPU capabilities from the cloud and use that for our computations. So that being said, hang on, I am getting some noise over here. I guess everybody is not muted right now. All right. So that being said, GPU programming is very similar to C++ and CUDA programming. Like, when I say CUDA, it is very similar to C++ and C programming. The difference is essentially the way it works is, we define an architecture which is called a kernel. And what really happens is, just to give you an example, for parallelization, if we have like a for loop in MATLAB or a C code, for instance, like, which is doing a matrix multiply and then some addition. So for this for loop, the way it's going to parallelize is we're going to remove the for loop and have it replaced by a kernel. And this indices are defined by a block and a thread structure. So depending upon how my thread is laid out in that kernel, so I have this index. And now instead of a for loop, I am still doing that matrix operations like a multiply and addition in this case, but it's happening all in parallel. So let's assume that my vector y is of size 10,000 by 1. So instead of running this for loop 10,000 times, now I launch like 10,000 threads with some architecture or definite architecture, like say we have 100 threads per block and we have 10 blocks, for instance. So that's why that's when my size of the Y would be 10,000. So and 10 blocks, and then all these threads running in parallel, and we get a much faster output. So MATLAB would actually help you automatically transform all your code from whichever, like the MATLAB, wherever it sees that this could be parallelized, this could be launched in parallel, it would do that for you and make this process very seamless, like this parallelization pretty seamless. So one of the things to keep in mind is a lot of time not everybody gets the speed up they want. Like even while scaling the code in the GPU, we do not get the speed up, and it's like the question is there, like what's going on, what's happening, and why are we not getting the speed up necessary? So one of the things to keep in mind is it is highly dependent on how we use the memory spaces. So this block and grid structure, which I'm not getting in details just now, because that's a little bit more digging into if you want to know more. But the way this structure is organized for launching those parallel threads and how it interacts with the GPU memory, like that shared memory versus the per thread memory and the global memory, we get different speedups. So for instance, the global memory fetching and rate would be the slowest versus uh, shared memory. So we would want to optimize the processes more and more on the shared memory versus doing it over like a uh, versus doing it over like a a global memory. But then also with the global memory, there's some overheads involved, like if we are to transfer the data from the RAM of a computer to the global memory of the GPU and whatnot. So this memory trade-offs are there in GPUs, and that's what we'll cover in one of the practices on how to better leverage uh, uh, like the GPU coder tools and how you can make them more efficient for these kind of operations. So without much delay, let's directly go to MATLAB. Again, hang on. Yes. So let's go ahead and start looking at the 7 practices. So let's start, at this point, I'll open MATLAB, and in the next 40 minutes, I'll try to cover these 7 scenarios on how you can better leverage MATLAB uh, for doing this parallelization. Guys, I'm sorry a little bit. I'm getting a lot of audio issues at my end, so that's keeping me a little distracted. It's maybe the feedback or something coming from my headphones, but so that's why I'm kind of like in between going on and off. So let me open MATLAB. So this is the MATLAB. Hopefully you can see my MATLAB screen. And this is the code I have for the simulation, which I just talked about, the case study. So a geophone array, transmitting signals, receiving back, and as it receives back, it generates an array, a matrix. So I won't go over the code. If you are interested in going over the code, I would be sharing the script with you. And if you're interested in learning more about this radar simulations, like, how do we do the platform, how do we do the motion, transmitter, collector, that's a discussion for another day, but it's all functions from MATLAB which I use. And I say that, this scene which I'm kind of simulating is a scene for 4 seconds for the motion of that platform. And after doing some initial processing, the image I get is something like this. So it's, I call it a pulse compressed image, but for those 3 targets, let me just run this section one more time. And by the way, guys, for those of you who are not familiar, the one script which you're seeing in MATLAB, this is called a live script, which has like nice features like, rich text formatting, images, equations, but then you also have the code embedded in the script. So it is a very neat way of representing MATLAB scripts, and it kind of like helps you rate and share your results in a much more orderly fashion, and it's more like a report representation. And even the images and that's are live in this code. So like I can zoom in the images, in the figures, everything. So you can see that for the 3-point targets. So I did move my sensors from minus 200 to almost like 200. Minus 200 to 200 meters, and then I got the returns throughout. But ideally, what I would like to see is image of something like this. So when I say image something like this, essentially like after my all this algorithm which I have been processing, what I really would like to see is now I don't see that parabolas, but if I zoom in on this region, let's zoom in on these 3-point targets. So you can see that this 3-point targets are very nicely converged to the 3-point targets. If I zoom in for instance, then you'll see that this is the center with some side lobes both in the x and the y plane, which is expected. But this is the algorithm we're looking at. So this which converts this pulse compressed image with these parabolas and focuses it onto point targets. So let's take a look at the algorithm, and then we'll get back to the subtleties or the 7 practices for the GPU. So this algorithm, essentially what happens is it is a ray tracing algorithm. So there are for loops, like, this one. So this is the script for converging that data. And what really happens under the hood is there's like a for loop for iterating to the range index. There's a for loop for iterating to the cross range index. So like, for loop on the X and the for loop on the Y, so that we can scan every pixel or every data point in the matrix. But then at between these for loops, we are doing some calculations, like, we're calculating the length of the aperture over here, for instance. Then we're calculating some more, like we're calculating what is the position of X, Y. And then there's another third for loop, which is actually we're synthesizing the synthetic aperture. Again, we don't have to go in the details what's going on, but really for every pixel point, we do a backtracking as if, where the ray is coming from. We compute some time difference, time delay, and then we call that, we add that, we apply the phase compensation based on that time delay. So, exponential 1j2 pi, the center frequency times the signal, and then we start adding those pixels on, superimposing those rays on one over the other over the other. So under the hood, what really happens is for any pixel, let's say, if a pixel is this, and over here, so what I'll do is I'll try to synthesize the aperture, like how the parabola would look like. And for each of these points, how the parabola looks like, for each of those points, uh, uh, like, at this pixel, I will synthesize a parabola. At this pixel, I will synthesize a parabola. At this pixel, I'll synthesize the parabola, and so forth. So for every pixel in the image, I'll synthesize the parabola. And then I will apply to the phase compensation for the data points, which is my signal, and then add them up. So that's what's happening. So add them up, add them up, add them up. So that's why when I see this, this nice parabola, like, the big ones, so I actually synthesized a parabola on top of this, and I added all the pixels so that all the data points converge in this nice point targets. But obviously you can see that, it's got 3 for loops, and the data size of the matrix, if you look over here, it's like, just for 400 meters is 2000 by 2000. So it is very, very huge. Uh, Very huge, because this is just, uh, uh, is there any questions? Uh, okay, yeah, I was again getting some noise. Uh, So as you can imagine, with the 3 for loops, and even just with a small, with a very small range of like 400 meters, I'm getting like a 2000 by 2000 matrix. But imagine the surveys which are done for this oil and gas exploration, they're like done for kilometers and kilometers. So the data size can go all the way up to like, this start going up to terabytes, and actually several thousand terabytes. So that would be like 2000 by say 1 million, 2 million, 4 million, and so forth. So that it gets very, very complex. So that being said, so that's a problem. And, obviously, so this is a candidate of parallelization. So what we can do is, because this whole algorithm that, at every pixel we're synthesizing independent parabolas, it can be parallelized, massively parallelized. And that's how we'll leverage on the GPU. So let's go to the number 1 approach, which is using a parallel computing toolbox. So now, using a parallel computing toolbox, if you just, open, let's say, Google, for instance, and you search, MATLAB, GPU, parallel computing. Let's just search that, and then a couple of links, but you'll see that, if you open to the main page, parallel computing, perform parallel computation on multiple core computers, GPUs, and clusters. So GPU is one of the workflows supported, which is the number 1 practice which we're talking about. And if you see this MATLAB GPU computing link, you will come across this page. Then it will tell you, like, uh, how automatically from MATLAB it would run on the GPUs. And let me actually quickly open the documentation for that matter. Uh, Let me just quickly open it up. Like, So I'll just do a doc search. Mm, Let me quickly open this. And really, like, this is the page I was looking for, the GPU computing in MATLAB. You can see that there's some key functions and there are some topics for you to take a look at. Feel free to take a look at them at your free time. But really, if you see the main functions, it's like things like GPU array, gather are the ways which we scale algorithms directly from MATLAB onto the GPUs. So the way it works is like any data on your MATLAB can be declared as a GPU array, and after that, any function applied on that matrix would be actually happening on a GPU. So let's take a look at this particular case. In this particular case, what I can do is, think about this. This algorithm is very complex in the sense of a lot of things going on, but just let's simplify things a little bit. Let's just say this algorithm was maybe a 3 or 4 step process, something like this. Let's say the algorithm, what it does is for every pixel, I need to do a phase transformation, which I'm actually doing in this case. Maybe I'm doing some kind of a cubing and addition, and then doing some like a let's say tan inverse or sine inverse or something like that. So for every pixel, if I'm doing like things of operation, so for every pixel I mean like every data point of this matrix C data, I'm doing these kind of operations. Then what I really can do is now I can the C data is lives on my MATLAB, like my CPU, but my computer actually has a GPU device connected to it. So, let me just run this GPU device command, and you'll notice that my computer is actually having a Titan X GPU with it. So what I can do is I can convert this data. I can convert this data over here and C data, and I say that, okay, let's make it a PCT data. So what that will do is now if you see the PCT data now, uh, now this PCD data is the same size of C data, but it is now a GPU array. So any operation I'll do on this data set is actually going to happen on the GPU. So what I can do is I can, because I already have this script, which does like, 3, 4 operations on the C data, and then finally S data is equal to A sine inverse of that. So what I really can do is, call a function called arrayFun. So for those of you not familiar with arrayFun, what it does is, we call this function, and I call this function for the matrix, which is 2000 by 2000. So what it really does is for arrayFun, like for every pixel of PC data or every data point, it's going to execute this function. So it's like a massively parallel process. It's going to happen all at once on the GPU core. And then finally, you call the gather command to get the data back from the GPU on your MATLAB workspace. So let's go ahead and run this. And I have a TikTok running, so I'll just do this run, and you'll see that, okay, in the first iteration, it only took me 2.2 seconds, but actually if I run it again, maybe you'll see that it might be a little bit more faster because now we have some cache memory associated. So 0.1 seconds. But on the other hand, if I call the same function like something like this using a for loop, which I have over here, then notice how long does it take. So it is the same function start process PCT, but now I'm calling one pixel at a time, like one data point, C data, C data, C data, II, and running a for loop of the length of C data. And for that 2000 by 1000, I see that, it takes me 16 seconds. 16 seconds. So 16 seconds versus 0.39 seconds. It's like, I don't know, it's 48 times speed up or 50 times speed up. So just with one GPU device, if you have it connected with your laptop or your desktop, and if you have these small operations happening, you can convert those matrices to GPU array, and using gather command and maybe arrayFun, you can scale those processing steps very quickly, very, very quickly, just in like 2, 3 lines of code, right? GPU array, arrayFun, and that's about it. And I put everything in the function. And now it's like, I get this massive speed up of 50 times for this computation, which otherwise in MATLAB can take very, very long. So this is one of the approaches, and this comes with the parallel computing toolbox. Now, the problem with this approach is it has to be, all these operations has to be strictly like they have to be very strictly monotonic and linear. What I mean is like all these processes on the pixels need to be very, very independent. And it's not like one pixel data can be dependent on the other one for any like a data exchange or between one pixel and the other pixel. So that does draw a limitation. The GPU array will give an error because it wants all the operations on all the pixels to be strictly independent of each other. But in our case, in this particular algorithm, if we go back to the algorithm at this point, you'll see this line where we're adding the pixels. So you remember we had created those parabolas, and we are actually for one pixel, any point of this, we're adding these all points on the parabola. So it's not really a strictly independent. There is some dependency where for inside this innermost for loop, we do want to have this count equal to count plus kind of operation going on. So the value at this place is dependent on the previous iteration and the next iteration. So it is dependent. So that's where this approach gets a little limiting, and that's where we move on to our next approach, which is the second best, point number 2 for our best practices, which is speeding up the algorithms by generating CUDA code. So let's go ahead and do MATLAB again. And this again is a very, very simple process. So what I can do now is because I cannot use the GPU array in this case, but what I can do is I can convert this whole function into an optimized CUDA code directly. And the way to do it is using the GPU coder app. So let me show you what I mean. So I can do it with a command line, but then also there is an app. If you go to this app and a drop-down menu on the app, you'll see that there's an app called GPU Coder. Let me open this real quick, and I'll actually show it to you live, what I mean and how easy it is. And this is a path towards deployment too. So let me say, so this GPU Coder app kind of gives you an interactive way to convert your MATLAB scripts functions, which is running in serial automatically in CUDA code, which will run in parallel on the GPU. So, the first step is enter the function name. So the function name is tdbp. All right, that is good. I'll just do it in front of you. And then it says that, what are the input data types? Now why does it ask the data types? So this is my data types, like, the input data, C data, radar param, cross range, fast time. So it does ask the input data types because C++ and CUDA are loosely typed language, and we need to define if it's a double, if it's an integer, or if it's what. So one way to do it is these variables are on my workspace. So I'll just directly go and type the values. Like, oh, I thought there's a question. If you guys have any question, please feel free to post it in the chat or interrupt me in between. Like I said, we want this session to be useful for you so that you can leverage it, after today's talk and apply it in your project. Yeah, so I was saying, we want to define the types. So C data is a variable. Now automatically when I put C data, it said that, okay, it is a complex and double of size of this. Similarly, I'll do the same step for radar param. These are the parameters, like the center frequencies. It's like a structure with the double arguments. Cross range is my x-axis, which is my distance of x-axis, and fast time is actually my y-axis. It's a two-way travel time, and you can see that it automatically picks up the type like a double 1 by 2000, double 1 by 1. So let's go ahead and do next. Taking a while. All right. So now it gives us an option. What would you like to do? You want to generate a source code. You want to generate MEX. You want to generate DLL or .libs, or you want to generate standalone executable. So with GPU Coder, you have all these options. You can generate a source code if you would like to integrate with an external project, or if you want to run inside MATLAB, you can generate a MEX. Then you can also generate like DLLs for external linking. And then if you would like, you can also generate the main file, main.cu file, to generate a standalone executable so that it runs on the operating system outside MATLAB. So for this particular case, we would generate the MEX because we still want to, our goal is to speed up the algorithms on MATLAB. So, we would go ahead and generate the MEX in this particular scenario. So let me go ahead and choose that. And I'll just, without any much delay, I'll just go ahead and say that, okay, let's just generate it. So, it is generating. It takes a while to generate, but I already have generated it. And let me show you the report. So if it allows me to open, what it does is automatically, when I say generate, it finds out, okay, this is the code. Where are the places where I can parallelize? Like, there's like a for loops, I can parallelize those. There's like a matrix operations like multiply, or, vector operations like divide, multiply, and stuff like that. I can parallelize those, put it on the kernel. So that's what it's going to figure out. But at the same time, it would also generate a version, like a compiled version, which can run on MATLAB. And that's what I call the MEX file. And we will run the code in MATLAB on the GPU. And I'll show it to you in just in a bit. It is still running, so maybe we can give it just a minute. I was hoping I can open the previous report, but I think I missed it. So we can just wait for this to run. But what you'll see is this CodeGen folder would create, in this case, I'm creating a MEX. So it would create the sartdpp function name, and it would be building these files. Like you can see that there's a sartdpp.cu, sartdpp.h, data file, initialize, terminate, and all those source code. So I think the process is complete. So let's go ahead and take a look at this. Oops, oh, no, it's still building. Yes, it is built. So if I go to the report, you'll see that, now I have the standalone code, which is a .cu code. And if you see the sar.tdpp, these are the kernels which it created automatically. So this kernel is running in parallel. And if we inspect a little bit more, it is the same code. It's got those rounding and everything which I was doing in that function. But with the exception that in this case, we have this for loop, the outer for loop, we have the inner for loop, but we only have like two for loops. So what it did was it actually minimized. So what it did was it actually removed one of the for loop and massively parallelized this operation in that fashion. So, this is the report which it creates, and this is a sardddpp .cu code. Like all the source code is right in front of you. And this source code, the CUDA code, is actually the one which runs on the GPU. But because we generated a MEX, so what it is we've got a compiled version of this code running on the MATLAB. So if I were to running on the MATLAB, so the way it works is, in the interest of time, so I do call the sartdpp function on the CPU, and I call a tick-tock command on it. So, that runs just on the CPU. But after generating this CUDA code, now what it did was it created the sartdpp_mex, which is my executable file, which is over here. Let me show that to you so that, you can trust me that it was just generated right now, sartdpp_mex. My original function was sartdpp, but now I have a MEX version for it. So I'm going to run both these functions and with a tick-tock like sartdpp_mex and sartdpp on the CPU as well on the GPU. And if I do the visualization of the results, I did it beforehand, before getting on the call. So if I do the plot, then I see that, that the time execution for the CPU version is 273 seconds for this algorithms, 273 seconds, whereas the MEX just got executed in 7 seconds. So how cool is that? I mean, cool in the sense like two folds. First of all, you have this MATLAB function. You did not need to change anything at all. You went to the app. You said that, hey, let's open the GPU Coder app. I don't know what needs to be parallelized, but it's you specify the function name and you just walk through the steps, like specify the function name, define the input types, and then just click generate. You get automatically you get the SAR TDBP underscore mex, and just without anything, without any understanding of what CUDA is, what GPU is, what is parallelization, without any knowledge whatsoever, you can generate this mex. MATLAB does it for you, and you get the speed up of 273 seconds versus 7 seconds, which is like, I think it's almost what, 8 times speed up, or okay, my maths is, I guess it's, my maths is going all funky right now. I think it is 40 times speed up. I guess, yes, it's 40 times speed up. So 40 times, that is like huge, huge. Imagine my background is radars and I've done ultrasounds for the last 5, 6 years now. And I've spent like, I've had algorithms running like overnight and even like for the entire weekend on MATLAB. And when I come back on Monday, I see that it's still running, and that's a lot of pain. But with this GPU Coder tool, I can massively scale it up directly on the GPU, and then one GPU on my machine, and then it just happens and starts happening in a few seconds. So this is huge. So this is that. So this was the second practice. So first one being running on the parallel computing toolbox, but the second one being automatically generating the CUDA code. So those are the two main important things, and the rest things would be really quick, and I'll show you in a very quick fashion. So the third thing is optimizing the generated CUDA code. So let me open this, optimizations. So what does it mean? Now this is where a little bit of CUDA understanding comes into help, and what really it means is now that we have automatically generated the CUDA kernel, and we got this execution time in this case of 7.5 seconds. The question is, can we further reduce this time? And the answer is yes. There are a lot of ways, a couple of ways, actually not a lot, a couple of ways. MATLAB gives you the flexibility if you would like an optimization in a certain format. You have the ways to do it. And what we call in MATLAB is, if you go to the doc again, like let me just do a Google search, GPU coder, optimization, MATLAB. So if I just search something like this, I think, let's go to the GPU coder doc page. And if you see this, uh, like kernel creations, like let's say open this section, kernel creation, then what you'll see is that, you have these pragmas like coder.gpu no kernel, coder gpu.kernel fun, coder.gpu kernel, code GPU coder batch matrix multiply, strided matrix multiply. So these are like optimized GPU implementation of a batch matrix multiply operation, optimized GPU of strided and batch multiply operation. So these are the libraries like which is provided by NVIDIA and the GPU providers, and we directly implement it. And what this does is even for those matrix multiply operations, which we did create a optimized CUDA code, we can further, modify it. Further, we can enhance it. So just to give you a quick example, in this particular case, for instance, let me open the script real quick. So in this particular case, what I did was for the same, actually I increased the data size for this particular example. Now it's not 2000 by 2000, it's 2000 by 10,000, which is totally fine. But, the algorithm is still the same. But, I say that, okay, without any modification, if I generate the raw CUDA code, because my matrix size has increased, it took me like 71 seconds. So even with that increased matrix size on the GPU, it took a pretty long time. But then I can say that I can force a kernel generation. So what really that means is, I can have one of those pragmas. Again, I won't go in the details. If you'd like some detailed discussions on this, then feel free to reach out to us. We can have a very detailed discussion on each one of these. But, I just want to keep it at a high level right now and make sure you understand that this option is available, so that if you get stuck, you can do a Google search and come to this option, or reach out to us asking that, hey, that day you talked about some optimization, where can I find those? And then I would be more than happy to point you. But just to give you an example, so in the second section with the we use this pragma coder.gpu kernel. So we enforce GPU coder to generate a kernel for this for loop. So by placing this pragma, if we again generate the code, and now from 70 seconds, the time has reduced to 10 seconds. Similarly, there are ways we can optimize the MATLAB code, for instance. Not only those pragmas, but we can optimize some MATLAB code. So let me show you this optimization real quick, and then we'll move on to the next one. When I say optimize the MATLAB code, what I did was I cleaned up a little bit of code which is between these two for loops and placed it over here because I can totally do that. And now MATLAB automatically combines both these for loops as one and generates a kernel for both of these for loops instead of just one for loop. So when I do that, uh, let me go back to the script. I further reduce my time to 7 seconds. So you see how it's kind of optimizing. And then finally, we can optimize the way the kernel is called or the grid structure. Remember, I said that the memory is one of the things, like going back to the slides, how we distribute the memory and how this block and grids kind of are laid out. So that's how the kernel is called. So we can optimize this. So what really that means is, in one of those pragmas, let me actually show it to you real quick. So in one of those pragmas, GPU kernel, you can actually define how your grid and block structure looks like. Like in this case, I say that, hey, my grid structure has, there are 1024 threads in each block. And in the grid, I have a 2D structure with 1024 versus 1024 blocks in one grid. So kind of, I set up some parameters based on the data. And, as you can guess, this would give me a further speed up. Now from 7 seconds, I went down to 6 seconds. And then finally, last but not the least, now we can use GPU arrays in together with GPU coder. So this is very important, guys. So GPU array was the technique number 1, which I showed you. GPU code is the technique number 2. But in technique number 3, there's another way that, because memory transfer and overheads takes a lot of time. So if you're just strictly thinking about MATLAB or speeding of algorithms in MATLAB directly, then you can leverage both these approaches. So what I do is I create GPU arrays for the data and then do the code gen of the function. So for the data, like the input data types, which were going like the C data and all, I still do the GPU arrays and do the GPU code gen and look at this. From 70 seconds, I've gone to 0.1 seconds. So both these functionalities together would give you the best result, parallel computing as well as GPU coder. But again, this is a huge data set. So with this GPU array, I do optimize the memory transfers time. And this is the one why I'm getting this huge speed up of 0.818 seconds. So as you can see, so the best practices number 3 is buy a couple of these. Again, you don't have to remember all of them today, but with a couple of these modifications, with the GPU code gen, you can go from 71 seconds by default, which you might be getting, to a final image, which still looks like it's 100% correct, but you get a speed of 0.1. So even on the GPU, you can further optimize it, and that's the best practice number 3. So moving on, hopefully everything is good so far. I don't see any questions, but I'm sure if you are listening, you might be thinking, and if not today, then please feel free to follow up with us on a later day, whatever you need with the trial licenses, you want to try out GPU Coder, or you already have some MATLAB routine and you want to take our help in parallelizing those with GPU Coder or parallel computing, and you don't know which is the best approach, we would be more than happy to come on board and help you with those things. So that being said, I have 5 minutes left, and these things I'll just cover at a high level because these are more, I just want you to make you aware that these things do exist. But while I'm going to cover this last 4 options, I also would ask you guys to, I'm starting a poll over here. So if I would really appreciate if you guys can fill up this poll question. So you would have got a pop-up saying that the poll started. So it's just some uh, uh, so it's just some questions like what would else would you like to hear from us? So please do fill in the surveys. These are very helpful for feedbacks, and then we can better help you and assist you moving down the line. How would you like to kind of like leverage uh, our specialty for making you successful? Of course, it's all about you. So while you're filling up the polls, I do want to cover this couple of things more. So let's go and see the fourth and the fifth option. So the fourth and the fifth option is how we can generate a standalone code and deploy it on the embedded GPU. So right now, until now, everything was happening on the desktop GPU, so that your GPU is connected with with your CPU. But a lot of our customers, and maybe some of us in the call, like people are developing medical devices, people are developing edge devices for Seismic, right? So the processing on the GPU is happening as the data is coming in real time. So how do you target those kind of applications with getting a good speed up? So it is very, very easily supported in MATLAB. And the way to do it is, let me open another script. I call it a Jetson script. So for those of you who don't know, Jetson Nano is one of the embedded GPUs provided by NVIDIA. Let me just do a Google search, Jetson Nano. So if you go, it's an NVIDIA kit and it looks something like this. So this can be placed on an aircraft. This can be placed on a, underground imaging device or a medical device, or, it's a very small device. It's a GPU. And MATLAB supports code generation as well as verification and validation workflows with this. So, I have the script. I was running it and playing it before the session, but I knew that this is a lot of content, so we won't be able to cover it. But really what I want you to remember is with the same GPU Coder app, I mean, we can do the things on a command line as well. So whatever I showed you on the GPU Coder app, with the same code, it's still the same code. It is the SAR TDBP, this particular thing. What I can do is I can generate uh, I can generate a standalone executable which runs on the Jetson board. And, the way it works is like I have a main.cu file. So, I can, along with the application, hang on a second. When I run this, when I generate the code for this SAR TDBP function, which is my entry point function, it, it generates not only the files like SAR TDBP.cu with the optimized parallel kernel, but then it also generates an example main file for me, the main.cu. So if I open it outside, MATLAB, like say in my Visual Studio, so this is like my function. It shows me that in my main function, like main, how this SAR TDBP is called. And, in this case, it is called like, hey, these are the, input data and then the parameters, and then finally S data is the output data. So this is all standalone. And now you can modify this main function. So it would be calling this RTDBP, which is running on the GPU, but you can modify this main function to be able to assign like read and write operations. So if the data is coming and streaming live, you can have this read function over here, like, in this case, this one is reading like a vector. So you can replace this by some read function. So for example, in my case, again, I don't have the time to show you, which was expected. But what I did was, let me open it outside MATLAB. So what I was working in a standalone executable, like, how do I stream the data? So what I thought is like, just for example case, what I can do is I can save the data as a text file, for instance. Sometimes text files, CSV files, binary files, there's so many different formats. And I replace it like, now I will be reading this data over here, like for instance. So now I'm doing a fopen and fread and fscanf to read the data. So I'm going to still run everything on the GPU, but I have, given it the read and write routines. And if I go and do a remote login, like so this GPU device is actually on my network, which is over here. So when I generate this code from MATLAB, it generates my executable, which is the sartdbp.elf on my GPU coder device. And now I'm away from MATLAB. So once I generate this, and this is the code which is living on my this machine. So this is like I've put it into this Linux machine, and it's got this ELF, and I've given the routines for reading and writing the data. All the data is in my, now it's in my remote build directory. In this particular directory, I have stored the data. But long story short, now I have gone away from MATLAB, and for the same SAR-TDBP, which was running on MATLAB, now it's running standalone on by embedded target. So what it means is if the data is coming in live, as the sensors are acquiring the signals, it is going to be processing live, and then I'm getting the results. So that is embedded deployment. But at the same time, before doing this EXE, we also have the option of processor in the loop. So if you would like to connect your GPU device with MATLAB and run it together such that the data, what happens is in the processor in the loop, you do it for verification and validation. And what really happens is now, instead of getting the data live from the hardware, first you would like to test it by synthetic data coming from MATLAB. So the PIL mode offers you the capability of connecting the hardware directly with MATLAB, streaming the data in the hardware, getting the results, processing it on the hardware, and getting the results back in MATLAB. And you can profile it like, hey, if the speed is enough or not, and things like that. So again, not in the details, but just remember that processor in the loop is another workflow. So that being said, really quickly in the last 2 minutes, the cloud computing capabilities, I just want to briefly touch upon that. So in addition, if you do not have a hardware device like a GPU device with you, you can access a GPU device from the cloud, from MATLAB Cloud. So as of today, MATLAB works with AWS, Azure, Google Cloud. You can also create your Docker file image on the cloud and leverage MATLAB from that. So it is there is these sessions, like for the cloud computing, it's a full blown session for an hour because there's a lot of things to it. But just to give you I just wanted to give you a quick highlight is once the steps are highlighted on the documentation page. If you just do a Google search, MATLAB cloud computing. So if you just do a Google search, then the first link you come across, MATLAB on the cloud, is the one which we're looking at. And then you can see that we've got links on how to create a Docker or how do you access these public clouds and stuff like that. So the information is there. But really what that will help you is with one license called parallel server, you can do something like this. You can VPN into a cloud machine like I have done right now. So this one is on the Amazon AWS. And using my MATLAB license, now I'm VPN'd into a virtual machine. And if I just do a deep GPU device, so I've launched a MATLAB R2020A, and now I have a Tesla, like a much more powerful machine, GPU machine on my MATLAB running on the cloud. So that is very easy to set up. The instructions are there on the web page. And if you would like to access the cloud capabilities, if you do not have a GPU with you, this is fairly cheap because you would be paying Amazon AWS for depending upon the hours you use this virtual machine, because it's just a remote desktop login, which I've done, right? And then I can start running the same things using the GPU device from the cloud instance. So it's now all virtual all over the internet. So you would be paying Amazon Web Services, but it's a lot much cheaper than buying a GPU if you do not have a GPU. So some of the capabilities on that front, I'll leave it for another discussion for another day. But if you'd like to leverage the cloud computing capabilities, again, reach out to us. This is one way, like, you set up this AWS account and remote into it. The other way is directly from your MATLAB, from your desktop MATLAB in your parallel options, you can like set up a cluster like on the AWS. So those are the two different options which I have in the slides. I'll share the slides with you, but you can start leveraging the GPUs available on the desktop as well as directly from the VPN, which I have over here, like a remote desktop on the cloud, on the Amazon AWS, and use the GPUs for your computation purposes. So with that, I am over time. Sorry about that. But hopefully this session was helpful. I will share the slides, and I have got the snapshots on how to generate code from GPU Coder app so that you do not forget. Uh, if you, I see like a lot of us have finished the polls, but for those who have not finished it, and if you want to provide some additional feedback also, this is a QR code. Please feel free to scan it and provide us the survey. We would greatly appreciate it. And these are the things which I had. The slides have some additional links like some free trainings like deep learning, Simulink, and whatnot. And like I said before, if you have any questions with GPU computing, it is a very hot topic these days. And it's increasing, it's rampant increasing. Like cloud computing got recently introduced in MATLAB 1 year ago. GPU Coder got introduced in 2017. So if you want to learn about the latest, greatest stuff and implement it for your workflows, like we had a gentleman in the chat saying that he was only using GPU arrays but until now, but GPU Coder is like a whole new world. So if you want some more, our technical expertise or our services, or if you'd like to do us to do something, then we have like consulting. We have guys like me who can help you ramp up. And then we have a tech support line. Feel free to reach out to your partners, techsourceasia.com or events at techsourceasia.com. And there's a telephone number, and we would be more than happy to help you with getting ramped up or, uh, getting details on anything you want. So with that, I would stop. And do we have any last questions? I'm still here. So if you have any last questions, please feel free to ask right now. I would stay here for another 5 minutes. But thank you very much, guys. And hopefully this session was helpful. Again, there's a lot to ground to cover, but this session is more tailored to introduce you to the topics and let you make you aware of the various options. And if you want to go with one of those options, we can have a follow-up discussions exclusively on that. So thank you, everybody. I do appreciate you guys staying and attending this session. I see most of us have filled up the polls. If you haven't, so you feel free to fill the polls right now. I am, I think like a few people have not filled up, so I would appreciate if you can fill that up as well. So folks, I am available for any questions. If you have any, let me know. So we have a question, like we have a couple of questions. So I would like to answer one of these questions. Like the question is, between the inbuilt function in parallel computing toolbox versus generating a MEX file, which one is faster, assuming both codes can run? So Levin, thanks for asking that question. That's a very legit question. Uh, I think the answer to this question is very algorithm specific. So in my case, I cannot run with the parallel computing toolbox. There was a limitation, but even if I could run, MEX file does have some overheads between transferring the data from the MATLAB API to the operating system level. So, from MATLAB API, which is at the top level, the data does go back and forth between the operating system. So it does have some overhead involved. So if you can get away with parallel computing toolbox, that overhead is still there, but it is handled by the MATLAB engine inherently. So that is usually a little bit more faster. So the long answer short, the parallel computing toolbox should be faster for a couple of operations, like which you can do with GPU arrays. But things which I'm doing, we'll have to use a MEX file. So thank you for asking that question. So we have another question. Is the recording of the session available? Yes. So after this session, I will send out an email with the slides. I'll also send you the MATLAB code, which I showed you today for your reference. and then we'll also share a recording. We have another question, how to use GPU Cloud. So Fahad, thanks for asking this question. Like I said, I did touch upon the GPU Cloud very briefly just to tell you that the capabilities are there. And because you're interested, I would say that you can start with this link, use MATLAB in the cloud. And you can take a look at this. If you would like to use the Docker image, then we have this GitHub page link over here, this GitHub, and it would walk you through the reference architectures on how to set up the Docker and things of that sort. But again, like I said before, this is a very intense topic because there are so many workflows like public cloud, AWS, Dockers, and so if you tend to get lost in this, like now I'm in a GitHub page and I'll tell you how to set up the Docker image, create the Docker image, how do you do all those things, like for instance, I want to uh, 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 like, I want to go to this, for instance, like a reference architecture, MATLAB on AWS, then you get through all these instructions and it gets really complicated. So if you have the interest, feel free to reach out to the TechSource people, and we'll set you up with one of our application engineers and have a separate one-on-one session about the cloud topics. So there's another question. So thanks, Fahad, for asking that question. And like I said, we'll be more than happy to follow up with you on that if you're still facing an issue. So we have the links. But there is another question saying that, is there a way for individual non-commercial use of the tools we presented today for private learning? So I think I can answer this question that, there is. Uh, for commercial as well as non-commercial use, you can definitely use our licenses. We have student licenses and other formats. We also provide trials if you would like to try out these products and make sure that this is the right way to go. But one of your account managers, Genus, they can definitely help you more in how to get these individual non-commercial versions of these licenses. So, somebody from TechSource would reach out to you on that question with further details. I do not know the full details on the licensing models for the ASEAN region. So, we would have you, like your account representative, reach out to you for that. Excellent. This is great. So, guys, any more questions? I do see a lot of people are still online. Uh, If there's more questions, please keep it coming. These are great questions. We'll be more than happy to answer them. So folks, those of you who are still here and are dialed in, just to let you know that, we have other resources. Like, again, I'm repeating myself, but for any of the topics which we covered today, if you feel like one or the other topic is of your interest, we can have a separate one-on-one session and have a deeper dive into those things and make sure that you are successful using the products, whether it be the cloud, whether it be the GPU coder, whether it be the parallel computing. There's a lot of different options to go in MATLAB for speeding up your workflows. And like we said before, we do want you to make you successful. So, please do reach out to us for any questions. Uh, so thank you, everybody. It seemed like everybody liked the session. I'm glad that this was fruitful. So we have another question is, what is the difference between acceleration by GPUs and acceleration by FPGAs? That is a very, very wonderful question. And let me see if I have a slide on that. I think I did, but oops, not in this version. Never mind. So FPGAs are also massively parallel, and it's actually even more so than the GPUs. Because now at the FPGA level, what we're talking about is we have eliminated any operating system. We have eliminated all those overheads about transfer of the data between the memory to the the logical unit and stuff like that. So it's like it's all FPGAs like programmable gate arrays. So it's like the hardware logic that is really really fast. So I think for especially when it comes to uh, uh, DSP and like signal processing kind of application, FPGAs are very powerful and they are very fast. Sometimes GPUs do compare with FPGAs, but the only problem in the FPGAs is, with those the kind of the app which I showed you, we cannot like signal processing algorithms. It does take a little bit of work to actually realize that Simulink or MATLAB code or even like a DSP code for filters and stuff and convert it to a VHDL and then realize it on a hardware like a Xilinx board or something. So there's like a couple of steps involved and it does require some sort of expertise in the area before you can actually start realizing your models in FPGA. On the other hand, GPU coder, no matter how many filters or how many complex logic you use, because it's still happening at the operating system level, that's why we can generate code like a CUDA code really quickly, automatically, and within one a few clicks of button, you'll get the optimized CUDA code. So it's a lot more easier that way. But yes, I mean, FPGAs is still a good tool of choice by most of the DSP industry where the data rates are very high because of the massive parallelization it offers. And yeah, but like, the time to market is pretty long for those things. So uh, so we have another question is, would the coding involved in the tools subject covered today be applicable to quantum computing simulations? Uh, I would like to learn a little bit more on that. So, Genus, do you mind unmuting yourself and explaining, if possible, uh, what kind of uh, what are these quantum computing like? Is it more from a physics based or something? Uh, Genus, would you like to speak up? Like, feel free to unmute yourself and share insights if you would like to. Uh, it seems like you prefer not talking, but that's fine. Again, I'm just, oh, there's an audio problem with the mic. No problem. No problem. We can follow up again later, but if it's, I've just started Googling, if it's more about, it's still under the hood, some sort of a differential equations or some matrix computations or, depending upon how these uh, quantum mechanics and all are engineered and defined in your MATLAB, if it's those matrix operations, I'm guessing under the hood, there still would be some differential equation, linear algebra kind of operations happening under the hood. And definitely you can leverage the GPU workflows for speeding up and getting a results a lot much faster. And it seems like, there are very heavy computings involved in from these images, what I see for these quantum computations. So definitely, I guess GPU should be a tool of your choice, and you can leverage it in MATLAB. So we have another question. Are the GPUs faster than FPGAs despite the expertise required for DSP? Uh, Honestly speaking, I would say, like, in my experience, because FPGAs can be very, very powerful depending upon what FPGAs are using. I worked in a radar laboratory where we developed those radar systems for uh, sounding the glaciers in Greenland, Antarctica, and that kind of stuff. But all our radar systems were on the FPGA, and those FPGA boards were like really, really powerful. So we were processing data at the rate of like terabytes per second, or things of very, very high throughput rate with a lot of processing going on. So especially with the DSP, I would say the FPGAs are still faster because they're very powerful boards out there. But as a part of my work, what I did was I had one of the algorithms deployed on a GPU, and it worked together with the FPGA. And that algorithm was a little bit more complex. It was just not straightforward DSP. It was involving a couple of more steps to it, and translating that algorithm to fixed point, and then from fixed point to a Verilog code, from Verilog code to a realizing on a FPGA target was virtually impossible at that point. So I did deploy it on a GPU, and we did still manage to get that throughput. So it was fast enough, I would say. So GPUs, if not faster, they are definitely, kind of coming close to the FPGAs. And we're again talking about the DSP applications in this case. But for things like, what I did not cover today was like deep learning, machine learning, AI. For that, GPU is the tool of choice. MATLAB supports it. And, training models, deep learning models, AI models, uh, GPU is, they can be massively, massively parallelized on the GPUs. And as of today, FPGAs are not supported for doing those training processes because for the very reason they don't have an operating system. So thanks for asking that question. This is excellent. These are pretty great questions. Uh, I think we're 20 minutes into the session. We have some uh, really good questions asked, and it seems like everybody, you know, uh, uh, would like some sort of follow-ups. I was going through the polls right now, so thank you very much. I think I'll end the call at this point. Uh, like I said before, my name is Akhilesh Mishra, and feel free to reach out to your account managers in TechSource, and they can also help you connect. If needed, you can connect with me directly, or there are more engineers on site in Singapore office too, who can help you with getting started with this GPU workflows and whatnot. And we would be more than happy to collaborate. And uh, I have a tendency to repeat myself multiple times, but again, I like to mention this at this point that we want you to be successful. And if any help you need, do not hesitate to reach out. We would be more than happy to help you. All right, guys. So I'm going to end the call at this point. I don't think there are any more questions coming. So everybody have a great day ahead. Take care. Stay safe. Bye.